When you see a cyclohexane molecule, it's easy to imagine that it is a rigid, flat, hexagonal structure. However, you can see that this is not the case if we take a look at its 3D structure. This is why we draw chair conformations, to represent the three-dimensional structure that we don't otherwise see using line diagrams. It's important to conceptualize that most line structures we draw are top-down views of molecules, but if we view them from the side, cyclohexane actually has a bit of a bent shape to it, as opposed to just being a flat, planar hexagon. We represent this side view on paper using what's called a chair conformation. Here are all the different conformations of the same cyclohexane molecule. Most organic chemistry courses will focus on these two, the chair conformations, as they are the most stable. However, why is it that so many different conformations exist for the same simple molecule in the first place? Again, this is because the cyclohexane ring is not rigid. Atoms can rotate about their sigma bonds and produce alternate conformations. In this animation, you can see how all the different chair conformations that you will encounter are formed by rotating about bonds but not breaking any. Let's start by drawing our own chair conformation of cyclohexane. I start first by drawing two identical diagonal parallel lines. Notice that if you were to draw an imaginary line between each of the ends of these lines, they would be flat and equal in length. However, if you were to mark the midpoints of these imaginary lines, they would be staggered from each other. Next, I draw diagonal lines inward from the first set of lines until you reach the midpoint. Repeat the process for the other side of the chair. Notice the three pairs of parallel lines that are created during this process. Keeping these sets of lines parallel is the key to drawing neat chairs. We're almost done. Next, fill in the substituents on your chair. Just follow a tetrahedral geometry on each carbon to ensure that you are drawing substituents in the right directions. You can also use a molecular modeling kit as your guide. In this case, every substituent is simply hydrogen, so it is optional to draw these in. Now, let's try to draw something more complicated than just cyclohexane. For example, trans 1,2-dimethylcyclohexane. The first step to drawing a chair for any molecule is to draw the basic chair shape that I just talked about, and leave the substituents blank for you to fill in. Then, number each carbon on the line structure and your chair. You can choose these arbitrarily. Now, taking a look at our sample molecule, the two substituents are both methyl groups. So, remembering that line structures are top-down views of the molecule, one methyl is going out of the plane, and the other is going into the plane, represented by the wedge and the dash. Therefore, if we were to draw a side view of the molecule, which we now know is referred to as a chair conformation, wedges should be pointing upwards, and dashes should be pointing downward. This always applies. So, on my chair structure, since there is a wedged methyl group attached to carbon 1, I will represent it as pointing upwards. The dashed methyl group is attached to carbon 2, so I will represent it as pointing downwards. You can either draw in all of the hydrogens, or simplify the molecule down. That's your first chair conformation complete. I will now perform what is called a chair flip, which is just the interconversion between the first chair form to the other. If you would like to revisit how this process occurs, you should rewatch the animation that we looked at earlier. The first step to a chair flip is drawing a basic chair shape, except this time, draw a mirror image of the first one that you drew. Again, based on the concepts shown in the animation from earlier, I know that this carbon is carbon 1 from the first chair. Number the rest of the carbons accordingly. Now, draw in the substituents, as before. You'll notice that in the first chair, both of my methyl groups were pointing vertically, while they are now pointing in the plane of the cyclohexane. We use the terminology axial to refer to substituents pointing vertically in a chair, and equatorial to refer to substituents pointing horizontally. Remember that these two are actually the same molecule. When we perform a chair flip, we aren't breaking or forming any new bonds. Generally, the equatorial position is more stable than the axial position. So, the chair conformation with more bulky substituents in the equatorial position will be more stable, in case you are asked to identify this on an assignment. This is because of an interaction called 1,3 diaxial strain. There is steric interaction between this methyl at carbon 1 and the axial hydrogens at positions 3 and 5, which makes this chair less stable. The same can be observed between the methyl group at carbon 2 and the axial hydrogens at carbons 4 and 6. Conversely, on the second chair with the methyl groups equatorial, this interaction is absent. So, for this simple molecule of trans 1,2-dimethylcyclohexane, this is the most stable chair conformation. It is important to note that these are just two of the correct chair conformations for this molecule. If you were to work backwards and draw a line structure from any correct chair structure, you will produce the same line structure. Try it yourself. This is because, once again, they are just different ways to represent the exact same molecule. There are no bonds being formed or broken here. That's all for this video. I hope this was helpful.